I'll have solutions for you on that day. Solution guide. In addition, there's been a study guide. You know, you always should keep yourself up to date with Google Classroom. I'm putting stuff there all the time, comments all the time, things all the time. So yesterday, I posted a notes review, like a teacher review of the whole unit. It's not mine. It actually comes from the College Board. They give that to us. So it's a full review of the whole unit that I recommend you use, look over. Not like you have to necessarily read every single part of it, but it's up to you. It depends on where you're at. But that's there also. And is there anything else to say? I don't think so. All right, so I'm going to start the review now. I mean, other than we're going to have the exam next week, like I had already said. I think I'm going to actually do. The exam is actually going to be the AP Classroom. I'm going to use the AP Classroom as the exam. So students in school next week will have it in class with your Chromebook in the lockdown browser on Thursday, and then the following Tuesday will be the other group. All right, and so we have Monday through Monday and really Wednesday to review. Well, starting this weekend, you begin review. All right, I'm gonna go over those now. Is that already open? Oh, give me a second. So at least because Google Meet doesn't offer the whiteboard like Zoom does, so I did figure out a way I'm going to be getting the software. I'm in a trial mode right now, but I'm going to purchase it, so it allows me now to display my my iPad instead of using that drawing pad that I didn't like so much. All right, so I'm going to go over these now. All right, so the question involved a projectile motion problem. The launch angle was 60 degrees. The launch velocity was 20 meters per second. And we're going to be asked to find things like how long is it in the air? What is the maximum height? What is the total time? Sometimes we just write T with a TOT underneath for the total time to reach that spot. There's total time in the air, total flight time. And then the range. It's a horizontal distance to where it lands. All right, and then again, the launch speed was 20 meters per second. So you always start usually by thinking about the components again of the velocity, since it's a two-dimensional launch. I mean, that's more like 45. I mean, it's really 60. I'm not doing a good job drawing 60 is more like 60 is more like that, where this would be Vx and this would be Vy. And there's your 60-degree angle. Okay, and in general, remember Vx is magnitude of V initial cos theta, and the initial y component velocity is magnitude of V initial sine theta. Not going to by any means go through the whole sine cosine definitions and do all that all year. We can't again. So I'm not moving forward. I'm not anymore. I'm just saying this is how it is. If you have a question, you can always ask me at a different time, but not in class. But this is the way we calculate the components. And so let's do that. The x component was 20. I didn't mean to say that. The launch speed was 20 meters per second. To calculate the x component velocity is 20 cos 60. Just remember that you have your special triangle now. I don't know why I'm drawing vectors. It's really just a geometry thing of a triangle. Not sure what's happening. Again, let me try this again. The numbers to remember are 1, 2, root 3. It's a nice sequence, 1, 2, 3. Remember, there's a square root over the 3. The 1 is the smallest number in the sequence, so it goes with the shortest line. 2 is the largest number in the sequence, so it goes with the longest line. And root 3 is the last one. Once you have that set up, of course, the thin angle over here is the 30. The wider angle over here is the 60, and that's the 30, 60, 90 triangle, right? So we're looking at cos 60. Cos is adjacent over hypotenuse. So I just look at my 60. I have to look at the 60, which is here, and think adjacent, which is 1, over hypotenuse, which is 2. So cos 60 is 1/2. So 20 times 1/2 is 10. So the horizontal velocity is 10 meters per second. Just remember that's constant. Because while this thing's going through the air, if we were drawing a free body diagram for it, the only force is the gravity force, the weight on the object. The weight is pulling down. And it's that gravity force that's causing it to curl in the downward direction. If there was no gravity force, it would just go in a straight line into outer space in that direction, never curling down. But again, there's only a vertical velocity in the downward. I mean, there's only a vertical force in the downward direction, the weight, force of gravity, and that's why Vx doesn't change, because we're assuming there's no horizontal forces, there's no air resistance, because that's the assumption that there's no air or that the effect of air is minimal. So Vx is constant. Right away, you'd say, well, if it was in the air in total for 1 full second and going and landing, total amount of time is 1 second. Someone said, what would the range be? Vx is 10 meters per second. The range would be 10 meters, right? Well, we can do that afterwards because we don't know how long it's in the air, but that's how you think about range. If it's in the air for 2 seconds, then it moved 10 meters sideways in the first second, 10 meters sideways in the second second. 2 full seconds of it being in the air should be 20 meters range. But it's going to be some number, but you're multiplying, right? You're multiplying Vx times t. That's technically the formula. X equals V times t for a constant speed motion. So just keep that in the back of your mind. Now we got to work out what the vertical velocity is. The vertical velocity is 20 sine of 60. Coming back over to our 60-degree angle on the triangle, 30, 60, 90 triangle on the left. Sine, since we're working with sine is opposite over hypotenuse. So find your 60, which is in the bottom left. Opposite is actually pointing over to the root 3. And then hypotenuse is 2, because it's opposite over hypotenuse. So sine of 60 is root 3 over 2. So we really have 20 divided by 2, which we know is 10, times root 3. So the y component velocity would be initial, I should say. Again, it's only the initial velocity, because a little bit later, when it's up here, let's say, on this path, up in this area, this y component right here is going to be shorter than this one. This one's longer. This one's shorter because it's losing vertical velocity because of gravity pulling it down while the vertical velocity is actually up. And any force that's in the opposite direction of something's movement, vertical in a vertical sense, will slow it down. So we, again, always put the I there to indicate this is the initial velocity, because some other time later, the y component velocity is not going to be 10 root 3. It's going to be some other number. We don't put the I under the for Vx because it's just a constant number. Don't have to say it's the initial value because it's always that value. Never changes. So 20 root 3, 20 over 2, which was 10. 20 divided by 2 is 10, so we have 10 root 3. I'm going to go to my calculator and type in 10 root 3, 17.32, approximately. It's an approximation. All right, so 17 points, that's the initial vertical velocity. They may not ask you again for numerical calculations. They might just say, what is the formula for the x component velocity? And initial, or not even initial, just what's the formula for the x component velocity? You have to know it's v, magnitude of v, cos theta. Or what's the formula for the initial y component velocity, v sine theta? Then problem might just have equations, and you have to find the right equation. But if they ask you to make the calculation, then you got to use it. You plug the numbers in. All right. So now, if we're interested in the total time to reach the ending spot, the total time that's in the air, there's two ways of doing this, and the easiest way is using this formula. One of the big three. You always come back to one of the big three. This is all written out about y-axis motion. This is y-axis motion. So remember that at the top, when it reaches here, all of that velocity is sideways at that instantaneous moment. You couldn't say that about any other spot. At any other spot, there is some y component velocity. Or down here, there is some downward y component velocity. Or over on the other side, again, some upward. There's always a y component velocity other than at that instant at the very top. Right here, all of the motion and velocity is to the left. I'm sorry, to the right. So it's 10 meters per second, right? We already know that. Someone just asked, what is the speed of the object at the top of the path? 10 meters per second, because we already got that in the beginning. There is no y component velocity. If there was a y component velocity, then you have to do trig, and you'd have to say, okay, this is 10 meters per second for this picture here. I'd have to work out what the y component is. Maybe it's 2.5 meters per second. And if someone then said, for this moment that I'm pointing to right here, what is the actual speed? You'd have to then use the Pythagorean theorem to work out the speed. Knowing that the horizontal is 10, the vertical velocity, you'd have to use this formula to find out what that vertical velocity is at some moment in time. They would have had to say, 1 second later, maybe, and maybe this is where it is 1 second later. But if they don't, and a lot of times they won't, usually at an AP exam, if they're going to ask them to be right at the top, what is the speed? It's just Vx, it's 10. So with that in mind, the y component velocity is 0 at the top. Why are we talking about this? Because the question was, what is the total time that it's in flight? If it takes 2 seconds to arrive here, then it just takes another 2 seconds to come back down for a total of 4 seconds. 2 seconds up, 2 seconds down. Throw it straight up in the air. 2 seconds up, 2 seconds down. It's symmetric with time. Doesn't matter if it's being thrown straight up or along a curved path. So since we're trying to answer the question, which is what is the total amount of time it's in the air, really we just got to figure out how long does it take to get to the top, and then let's just double it. For that reason, we're using the formula I've written down and applying this formula right now to the top and saying, well, at the top, there is no y component velocity at the top. The initial y component velocity would have been vi sine theta, by the way. I know it's a number, and I do have it here, but sometimes, again, they'll just say, what's the formula? And you have to work out which are symbols. This expression is VIY. And technically, you usually would put minus gt here, because the acceleration due to gravity is negative, because g is always pulling down as it goes along that path, and down is negative. So you would therefore usually put a negative here. So if they said, solve for the amount of time to get to the top, you'd have to solve this for t. You'd have to move this whole thing over to the left side as negative v initial sine theta, and then you'd have to divide by negative g to solve for t if you were solving for this piece here. And you'd say, all right, the formula for the time to get to the top, just to get to the top, and notice it's a negative. Oops, sorry, I wrote that in the wrong spot. Let me. I keep forgetting I'm on a trial, and I know I am going to buy this. In fact, I literally had it for 7 days. There's 1 hour left on my trial, just coincidentally. So what I just wrote down here was negative vi sine theta over negative g. Just you couldn't see it because of the icon there. I'm just pointing out the negative and the negative would cancel, right? Negative divided by a negative is plus. And that's the amount of time to get to the top. It could be the question, what is the formula for the time to get to the top? And you need to know how to derive. starting with some fundamental formula like V final equals V initial plus AT. That's called a fundamental formula. And then do some things to it specific to a specific problem and rearrange it and solve for something now that they're asking for. It's called a derivation. You're creating something. To derive something means to create something new from something more fundamental. In math, we call it derivation. Derive the formula for the time to get to the top. Oh, there it is. If they had said, derive the formula for the total time that's in the air, if that's the amount of time that it gets to the top, I don't know how long it is. I'd have to plug the numbers in. But if they said, we're not in number world, we're not going to do number world, we're just going to say formula world. What's the time to get to the top? VI sine theta divided by G. What about the total amount of time? Just multiply it by 2, right? So we could technically do that. And we can certainly do that, and we will do that. I'm just going to write this down over here so I don't lose it. That was the initial y component. So now we're just plugging numbers in. 2 times the initial speed. This is the initial launch speed, right? That was magnitude. That was the magnitude of the, right? Because that piece up there is VIY, which is magnitude of VI sine theta. That piece is what's up there. So that VI is the magnitude of V. It's 20. In this problem, I happen to say it was launched with a speed of 20 meters per second. Sine 60, all divided by, in fact, those negatives would have canceled. So in this case, you would just put, because you're solving for a total amount of time that's positive. Just remember that sine of 60, I think we had done, it was √3/2. So if you wanted to just take away the 20 sine 60 and insert 17.32, you could. We already worked that out on the side. So it's up to you. You know, it's the same as saying 2 times 17.32 divided by 9.8. Because sine 60 times 20 as one thing, we did already. That was on a calculator, 17.32. All right, so now, I mean, I certainly couldn't do that in my head. There are people that can do that in their head. Pretty remarkable. Times 2 divided by 9.8. I get 3.53. So the total time in the air was about 3.5 seconds. 3.53 seconds. Time to get to the top would have been half of that, about 1.75 seconds. All right. Any questions on that before I go to the next spot or the next part? The total time was 3.53 seconds. I'll just keep record of that up there. All right, so now the question was, how high does it go? The easiest thing to do for maximum height, which is usually referenced as H max in physics. The easiest, and again, we always come back to one of the big three, always do. That's why I call it the big three. In my opinion, well, not in my opinion, it's a fact that you need to have a formula that has distance in it, but there's 2 of the big 3 that have distance in it. The position formula, y initial equals y final. Oh, y, that's a distance, so that has distance in it. And then the v final squared equals v initial squared plus 2a delta either x or delta y. The delta x is horizontal displacement, which is a distance. Or if you wrote delta y, that's vertical displacement, that's a distance. So you've got 2 to pick from. You could use either of them and arrive at the answer. I don't recommend using the second one, although I did show it to you yesterday, and then I made a mistake on which I commented on the ratio. If you wanted to see that, you go back to Google Classroom. The steps I did were all correct. It was just I reversed the numbers. But my recommendation is always go with whatever's quickest, because at the end of the year, you only have so much time to complete this exam. And if you can do one problem in 2 minutes, but if you did it a different way, it would take 4 minutes, do the 2-minute way. Like, you have to save that amount of time if you want to get through the exam. This is the fastest way to do it. These are, I'm writing y component though. This is all written for y-axis. Why? Because they asked me to solve for the maximum height, and that's a vertical thing. So that means the formula has to be all vertical stuff. What is the y component velocity at the top? None. We already talked about it. It's 0. There is no y component velocity at the top. What is the initial y component velocity? It's 17.32. I mean, I'm just going to use a number now. It was 17.32. That was the initial y component velocity. So I'd end up with 17.32. Don't forget the square. That's a common mistake for students, is to forget the square there. Plus 2. The acceleration due to gravity is negative 9.8. Again, because g is always pointing down. No matter where it is on its path, g is in the downward direction, which is negative. If it makes sense to just turn it into a positive just for simplicity of a calculation, I do that all the time. Technically, it's negative. It's always negative. Even when you throw something straight up in the air and it pauses right at the top, at its highest point. And then that's a trick question AP gives. What's the acceleration at that point when it stops? Most people say, who get it wrong, say 0 because it stopped. No, acceleration due to gravity is always down. It's always negative 9.8, even when something stops at the top of its path. And so the last step now would be to solve for delta y. That's your unknown. So now we're down to algebra, as usual. 17.32 would have to be squared, and then it would have to be moved over to the left side. So let's do that. 17.32 squared, and then move it to the other side. I end up with negative 299.98 equals negative 19.6, because this piece is negative 19.6 times delta y. And now I just got to divide that out. Notice that the negatives will cancel because it'll be a negative divided by a negative. And I get 15.3. I don't know why I just put a 2 there. 15.3. Just remember, delta y is the vertical displacement. So when we go like this and say it started here, but it ends here, this is considered delta y. It's the vertical displacement between those 2 points. And well, if you're calling this h max, then that's the same, right? Those are the same. H max and delta y are the same. Just pointing that out. All right, so that's our answer, 15.3 meters. And then our time, total time was this. This was our total height. The last thing to work out is the range. The range is the full horizontal distance from from one side to the other side of the field. If this was a, I don't know, basketball or whatever, football. This is the easiest one by far. As long as you have the time worked out, just remember that the horizontal velocity is constant. It's always moving equal distances sideways across the field in equal amounts of time. It's an easy idea in my opinion. Graphically, the x position versus time is just linear. Vx versus time is just constant, right? It's just a constant number. The number 10 in this case. And the formula, therefore, is just a linear formula, x equals v times t, where this has to be the x component velocity. Again, if vx was 10 meters per second, and the total time to go around the whole thing was 1 second, then the range is just 10 meters, because it goes sideways 10 meters per 1 second. But it's never going to come out as a nice number. We know the amount of time is actually 3.53. So we end up with x, which really you could call range, right? I didn't mean to do that. This distance here is really messy, so let me just point out that your origin is always taken, where you launch it. This is your 0, 0 mark. So, if the ball is here, we would call that x. If the ball is here, we would call that x, the final position x. But soon as they're talking about over here, yeah, it's technically x, but that gets a new symbol, r, because that's the range. The range is the full distance. So, even though you have it as x, that's really r. It's the range. And vx is now just 10 meters per second times the total time that we had on top, 3.53 seconds. Seconds and seconds cancel. Meters will be our answer. 10 times 3.53, and we get our 35.3 meters. So let's just see. We have the total time in the year was 3.53 seconds. The maximum height was 15.3 meters, and the range was 35.3 meters. Those are our results. So now in the last minute, if you were willing to stay with me for 1 minute, I know we're out of time. If you have to leave, you can, but it literally only takes me a minute. My hope is to just show you that literally takes about 30 seconds. That's right. Give me a second just to move this. There it is. So here's projectile motion. Now I will just shrink this down and clear all this out. We're launching it at a 60-degree angle at a speed of 20 meters per second. Our predicted landing spot was 35.3. And just make sure that the air resistance is turned off, which it is. Air resistance is off. So we launch. Okay, and then if we were to check with our little meter here, shows the time to get to this point is 3.53 seconds. 3.53 seconds. The range is the distance horizontally 35.31. We have 35.3. And then the maximum height 15.29. 15.3. So it all checks out. Let me lastly say, if air resistance was on, and you were shooting something that wasn't aerodynamic, a cannonball is fairly aerodynamic, like a piano. I mean, nobody shoots pianos, but if you launch this with air resistance on and it's a big, wide object, it's not going to land in the same spot. The effect of air becomes significant, and it slows the Vx doesn't stay constant. It slows down from that air, causing it to not travel as far. All right, that's pretty much it. Are there any questions from any of you at all? Let me stop presenting. Yeah, just make sure you do what I was the practice exam. That's really important. So make sure you do that. Just know it's not going to take you 20 minutes. I'd say at least an hour. I mean, an hour to a regular exam is an hour and a half. An hour and a half exam. So it's supposed to be similar to a regular exam. So just know it'll take you a chunk of time. Remember, you also have the notes on there available to you. If you have questions, you can email me. Otherwise, I hope you guys have a great weekend, and I'll see you guys Monday. All right. All right. Bye, everybody.
Have a good weekend, Mr. Kurzak.
You too, Jaden. Bye, bud.
Thank you.
Have a nice weekend, Mr. Kurzak.
Thank you, Joey. How you doing, Joey?
Good, good.
We don't talk a lot. I'm sorry that I don't talk to you more, but I want to make sure you're doing all right.
Yep, I am going through the book right now. I'm reading chapter 2.
Just hold on. Actually, just hold on 1 second.
Yeah, sure.
Just because I'm going to stop the recording because, yeah, stop.